Good afternoon and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to do some examples related to the concepts of total probability and Bayes' theorem. One of the examples I'm going to do for you is one of the quintessential classics of probability theory and relates to a game show that's many decades old now. The game show was called Let's Make a Deal, and this fine gentleman was the original MC of the game show. His name was Monty Hall. And we are going to solve what is commonly referred to as either the Let's Make a Deal problem or the Monty Hall problem. The goal is to maximize your likelihood of winning a nice new car instead of winning a silly old goat in a game that Monty Hall had contestants play at the end of the game show each week. All right? And we'll do some other examples as well. Before we start, I want to remind you of the theorem of total probability and Bayes' theorem. We're going to use both of these through the day. The top relationship up here is total probability. The relationship on the middle of the page is known as Bayes' theorem. In all cases, my collection of events A1 all the way up through AM form a partition of my sample space S. And what that means is, first of all of the partitioning events A sub I are mutually exclusive, they meaning that they share no common elements with one another. And secondly, the collective union of the partitioning events equals the sample space. They are mutually exclusive and collectively exhaustive. In these two relationships, event B is just some other event made up of outcomes within the sample space S. All right. If you need to, pause the video at this point. Remind yourself of the mathematical formalism for total probability and for Bayes' theorem. And when you're ready, go ahead and move along in the video, and we'll start our examples. Okay. First example I want to do is the Let's Make a Deal problem, also known as the Monty Hall problem. Let's make a deal. This was the game of chance that was played at the end of each game show, every day, every week. It's been a topic of much controversy among the uninitiated, the people who have not studied formal probability. There is a precise answer to how best to play the game, what your best strategy would be. So let's do it. So at the end of the show, Monty Hall selects a contestant, and the contestant is asked to select one of three closed doors or curtains to open. So a contestant and at this point, the curtain or the door remains closed. So at the beginning of this game, Monty Hall asks a contestant from the audience, usually someone dressed in a crazy wild outfit, asks the contestant to pick or select one of three identical closed doors or curtains. All right? Behind two of the curtains or doors are goats. Let's make that look like a G. Behind two of the doors are goats. Behind the other is a car. Behind the other one is a nice new car. All right, after the contestant makes his or her initial choice, Monty Hall opens one of the other curtains and reveals a goat. Monty Hall then opens one of the doors the contestant did not select. Monty Hall then opens one of the doors that the contestant did not select and reveals a goat. All right, so the contestant is asked to pick a door or a curtain, and we know that behind two of the doors or curtains are goats, and behind the other door is a new car. Monty Hall then picks one of the doors or curtains that the contestant has not selected, opens it, and reveals a goat. He never, ever, ever in the history of this game show revealed the car at this point. Never, ever, ever revealed the car. He never, ever, ever at this point revealed the car. That is supposed to be a T and then an exclamation point. Monty Hall never revealed the car. That tells us with 100% certainty that Monty Hall knows where the car is. All right. The contestant is now allowed to change his or her mind. Remember, at the beginning of the game, the contestant was asked to select a door behind which they think the car sits. At this point in the game, after Monty Hall has opened a different door to reveal a goat, the contestant is allowed to switch or stick. The contestant is now allowed to switch doors or curtains if they want, and the contestant's final selection is then open. All right. After Monty Hall opens one of the curtains to reveal a goat, the contestant is allowed to switch or stick with their original selection, and whatever the final selection is, that door is opened, and your goal is to come up with a strategy to maximize your likelihood of winning the car. What is the strategy to maximize the probability of winning the car? In other words, at that last opportunity, when Monty Hall asks you, would you like to switch doors or stick? That's the question. Should you switch when given the opportunity, or should you stick with your original selection? All right, let's solve the problem. Before opening one of the curtains, before Monty Hall opens one of the doors or curtains. The probability that you have selected the door behind which there is a car is 1/3. Remember, the doors or the curtains are identical. And the probability that you have selected the door or curtain behind which there is a goat is 2/3. However, I need an E there. However, after Monty Hall opens the door, one of the doors or curtains, we have more information. We have more information, and this information affects the outcome of the game. It affects our strategy. This more information affects our strategy. And to be precise about it, the information that we have, the extra information that we have, is that Monty Hall knows where the goats and the cars are. Never once in the history of this game, I believe there's a new incarnation of the game currently. Never once has this game been played where the MC of Let's Make a Deal has revealed the car at that point in the game. So Monty Hall knows where the car is. That is very important information. We know that he knows. All right. Now I'll start doing some math. Excuse me. Let me try that again. GR is the event that goat is revealed. SC is the event that I selected the door behind which there sits a car. All right, SC, select car, GR, goat revealed. The probability, this relationship up here is the probability that the curtain behind which the car sits was selected given that Monty Hall has now revealed a goat. MH Monty Hall revealed a goat. I want to calculate this probability. I want to calculate the probability that the curtain behind which the car sits was initially selected by me, given that Monty Hall subsequently revealed a goat. All right. Let me define one more event. I'll need this in just a few minutes. Well, let me just write down the next step. I'm going to use Bayes' theorem. This is the probability goat was revealed given that I selected a car times the probability that I selected a car divided by probability goat revealed given that I select a car times the probability to select a car plus probability that goat is revealed given that I selected a goat on the first draw, or first selection, times the probability to select a goat. So this is the additional event that I need to define. This is behind which a goat sits. Okay? This is all Bayes' theorem. That's all Bayes' theorem. All right? Now, notice that selecting the car and selecting the goat equal the sample space of selection opportunities. All right? S is the sample space of selection possibilities, rather, and on my first selection, I either picked a curtain behind which sits a car, I selected the car, or I picked a curtain behind which selects a goat, I selected a goat. All right? It's either a goat or a car. Goats and cars are mutually exclusive, and they're collectively exhaustive of all of my initial possibilities for selections. Okay. All right. Let's piece this together. What is the probability that a goat was revealed by Monty Hall given that I selected a car? What's the probability that Monty Hall reveals a goat given that I initially selected a car? Well, it's got to be 100%. Monty Hall knows where the car is. He never once goofed up and revealed the car after the initial contestant selection. Moreover, what is the probability that a goat is revealed given that I initially selected a goat? What's the probability that Monty Hall reveals a goat at his step in the game given that I initially selected the curtain behind which the goat sits? Well, again, that's 100%. Monty Hall knows where the goats in the car are. That's the additional information that I have. That's going to help me come up with my strategy. So then, plugging this into my initial relationship, the probability that I selected the car given that Monty Hall revealed a goat equals 1/3 divided by 1/3 plus 2/3. That's 1/3 or 33.3%. All right? The probability that I selected the car on my initial choice, the probability that I selected the car on my initial choice, given that in the next stage of the game, Monty Hall revealed a goat, is only 1/3. Meaning that it's 2/3 likely that the car is behind the other door. All right. the probability that on my initial selection I selected the door behind which the car sits, given that Monty Hall subsequently reveals a goat, is only 33%. Therefore means it's 2/3 likely that the car is sitting behind the remaining closed door. My strategy is always, therefore, when given the opportunity to switch or stick, I always. That doesn't mean that I'm always going to win the car. It just maximizes my likelihood of doing so. If I switch when given the opportunity by Monty Hall, I have 2/3 chance of winning. The answer, proven rigorously using Bayes' theorem, is switch. Always switch. All right. Let's do another example. I've got a company that makes a single product at 3 different plants. And these plants are independent from one another. They're in 3 different states, different workers, et cetera, et cetera. All right, plant 1. The first plant makes 50% of the total parts, 2% of which are defective. All right. Plant 1 makes 50% of the total parts, 2% of which are defective. That means that plant 1 makes 1% of the total defective parts. All right. Plant 2. Plant 2 makes 30% of the total parts, 5% of which are defective. % of the total parts, 5% are defective. And this means that plant 2 makes 1.5%. And clearly that I'm getting that number by multiplying 30% of the total parts by 5% of the 30% that are defective. So 0.05 times 0.3 is 1.5. Okay? Plant 3. Plant 3 makes 20% of total parts. % of the total parts, 1%. 1% of which are defective. And likewise, this means that plant 3 is making 0.2% of total .2% of the defective parts. Okay. So the first question we want to ask is, what is the probability The parts are shipped out to various retail locations for sale, and only the company name is listed on the part. The plant numbers are not indicated on the packaging. So parts are shipped out to retail outlets. Only the company name is shown. Okay? All right. First question I want to ask myself is, a part is chosen at random by a customer. What's the likelihood that it's defective? What's the probability that it's defective? Well, that's a statement of total probability. Total probability looks something like this. All right. B will be the event that the part is defective. And A sub I is the event that the part was made at plant I, where I is 1, 2, or 3. That's a statement of total probability. So the probability of my customer picking a part that just happens to be defective is 0.02 times 0.5 plus 0.05 times 0.3 plus 0.01, that's a point right there, times 0.2. All right. Half the parts are made at plant 1, 2% of which are defective. 30% of the parts are made at plant 2, 5% of which are defective. 20% of the parts are made at plant 3, 1% of which are defective. This is 0.01 or 1%, 0.015, 1.5%, and 0.002.2% of the 0.2% likely that I'll have a defective part coming from plant 2, 1% likely that I'll have a defective part coming from plant 1, 1.5% from plant 2, 0.2% from plant 3. The total is 2.7%. All right. 2.7% likely I go into a store, pick a product made by this company, and the part is defective. I can get there by adding this to that to that. So my total probability of having a defective part should be more or less obvious at this point. All right. Okay. Next question I want to ask for this example is, if the purchased part, if the part that is purchased by the customer is found to be defective, what is the probability that it came from plant 2? I walk into the store, I pick up a part, find that it's defective. What's the likelihood that it actually came from plant 2? To do this, I'm going to use Bayes' theorem. I want to find this. What's the probability that if it's defective, the part was manufactured at plant 2? Use Bayes' theorem. All right, that is Bayes' theorem. And I haven't pointed this out, I don't believe, prior to this. But notice that in the denominator of Bayes' theorem, we always have total probability. Probability that my part is defective is found through this relationship, which is total probability. The denominator of Bayes' theorem is always a total probability relationship. So we can now plug this in. 0.05 times 0.3. 30% of the parts come from plant 2, 5% of which are defective. And the total probability of a defective part is 0.027. And that works out to be 0.556 or 55.6%. 55% likely, slightly over 50% likely that the part came from plant 2 if I discover it to be defective. Well, you'll notice that plant 2 creates the most defective parts. All right. In fact, if you add up the defective parts from part 1 and from plant 1 and plant 3, I only get 1.2%. So it's a little bit more than 50% likely that my defective parts will indeed come from plant 2. Okay? And if you wanted, you could do similar calculations to determine the probabilities that a defective part came from plant 1 or plant 3. Let's do one last example for the day. This is an important example. What we've got is a digital communication link. All right. We're going to transmit something on the left-hand side, we'll call that X. And we're going to receive something on the right-hand side, we'll call that Y. In between is the channel. It's what sits between the transmitter side of my comlink and my receiver. It might be free space, for example, your cell phone's talking to a cell phone tower. It could be an optical fiber connecting one cell tower to another cell tower. It could be a coaxial cable. Could be anything. All right. So the channel will affect the quality of the transmission overall. X has two possible values. X0 will be 0. X1 is 1, meaning I'm going to transmit ones or zeros. It's a digital communication link. All right? 0 or 1. Y, my received values are going to be Y0, which will be a 0, and a Y1, which will be a 1. All right. Ideally, if I transmit a 0, then I receive a 0. And if I transmit a 1, then I receive a 1. However, due to channel noise, and the noise depends entirely upon the channel. Optical fiber links are very noiseless. Coaxial cables are medium kind of noise. Free space channels are, in some cases, quite noisy. Based upon channel noise, we will make some mistakes. Sometimes we'll transmit a 0 and determine a 1. Sometimes we'll transmit a 1 and determine a 0. Due to channel noise, we'll make some errors at the receiver from time to time. All right. Let's define some variables here. Let's let P naught equal P naught equal the probability that I receive a 1 given that I transmit a 0. This is probability, send a 0, send 0, receive a 1. All right? P naught is I send a 0 and receive a 1. P1 will equal the probability this is going to be the probability that I send a 1 and receive a 0. We want P0 and P1 to be small because these represent errors. All right, and likewise, Q0 equals the probability that I receive a 0 if I transmit a 0. It's probability that I send a 0 and actually receive a 0, and Q1 equals probability Y if X1. That's the probability that I send a 1 and receive a 1. I want Q0 and Q1 to be large. All right. you'll notice that in all cases, P0 plus Q0 equals P1 plus Q1, and that's 100%. In all cases, no matter what, if I transmit a 0, I will receive a 0 or a 1. If I transmit a 1, I will receive a 0 or a 1. It's a digital communication link. I can only send 1s and 0s, and I can only receive 1s and 0s. Therefore, P0 plus Q0 equals P1 plus Q1. In both cases, that equals exactly 100%. All right. Now, on the transmitter side, the probability that I send a 0 equals the probability that I send a 1, and that's, in general, it's about a half, at least over long communication lengths, over long duration communications. In other words, if I just observe the bits, the 1s and the 0s coming out of the back end of a computer that's part of a digital communication link, half the time I'm going to send 1s and half the time I'm going to send 0s. So the probability of transmitting a 0, equals the probability of transmitting a 1, and that equals a half. And I'm going to assume now, so that I can solve the problem, I'm going to assume that P0 equals 0.1 and P1 equals 0.2. All right. P0 and P1. These are probabilities of making errors. P0 is the probability that I send a 0, receive a 1, and P1 is the probability that I send a 1 and receive a 0. This entirely depends upon the channel. These probabilities can be calculated precisely if we fully investigate and understand the channel. That's a topic for a later, far more advanced course. You may run into this when you take a communication theory course, and you may run into it if you take some graduate courses in fiber optics or radio theory or radio propagation. We're not going to get into calculating these probabilities now. We're just going to use them. All right. So let's make a couple of calculations. What I want to find is the probability of receiving a 0 and the probability of receiving a 1. All right? I know that I'm, on average, going to transmit 1s and 0s each about 50% of the time. What's the likelihood of receiving 0s and 1s on the receiver end? To do that, I need to find Q0 and Q1. Q0 is probability of receiving a 0 if I transmit a 0, and that's going to be 1 minus P0, and that is 0.9. And likewise, Q1 equals probability of Y1, probability that I receive a 1 if I transmitted a 1, and that is 1 minus P1, and that's 0.8. All right? So, using the concept of total probability, I get this. This is total. That's total probability. And quickly, this is 0.9 times 0.5 plus 0.2 times 0.5, and this works out to be 0.55 or 55%. And likewise, also using total probability, the probability of receiving a 1 is the probability of y1 if I transmit a 0 times the probability of transmitting a 0 plus the probability of receiving a 1 if I transmit a 1 times the probability of actually transmitting a 1. Once again, this is a statement of total probability. 0.1 times 0.5 plus 0.8 times 0.5. And this is 0.45 or 45%. All right? All right? These relationships result in probabilities of 1s and 0s that are not 50%. So it's not 50-50 due to channel noise. Again, channel noise can be precisely calculated and predicted based upon a good solid understanding of the channel. That calculation is more advanced than we're going to get access to for this particular course. All right, let's use Bayes' theorem. If y equals 0, what is the probability that x was a 0? In other words, if I receive a 0, what is the probability that I actually transmitted a 0? If I receive a 0, what's the probability that I transmit a 0? I'm going to use Bayes' theorem to get access to that. Remember that the denominator of my Bayes' theorem is always total probability. Okay, so this is Bayes' theorem here. All right, we're using Bayes' theorem to do this calculation, and this is 0.9 times 0.5 divided by 0.55, and that is 0.818, about 81.8%, about 82% likely that if I receive a 0, it's about 81.8% likely that if I receive a 0, that I actually transmitted a 0. And likewise, if y equals a 1, what is the probability that I actually transmitted a 1? So if I receive a 1, what's the probability that I actually transmitted a 1? Once again, I'm going to use Bayes' theorem. Total probability goes into the denominator. We calculated that on the previous slide. And this is 0.8 times 0.5 divided by 0.45, and that is 0.889. 88.9%. Okay? It's not 100% likely that I will receive, it's not 100% likely that if I claim I receive a 1, it's not 100% likely that I actually transmitted a 1. That's because of channel noise introducing errors into the process. Final calculation. What is the total probability of error? Okay? Some people call this the bit error rate, or BER. I don't like that. The probability of error is the probability of making an error. It does not tell me how frequently my bits are in error. If I calculate a probability of error of 10%, that does not mean that every 10th bit is in error. It just tells me for every bit, it's 10% likely that I'm going to make a mistake. So we're going to use probability of error. Probability of error looks like this. It looks like, but is not, total probability. Probability of error is, let me write it down first. All right. If I transmit a 0 and receive a 1, that's an error. All right? If I transmit a 1 and receive a 0, that is an error. All right? So what I do is I take two conditional probabilities, the probability that I receive a 1 given that I transmitted a 0, and weight that by the probability that I actually transmitted a 0. And add to that, because they're independent of one another, I take the conditional probability that I receive a 0 given that I transmitted a 1 and weight that by the probability that I actually transmitted a 1. Add those two together and I get the probability of making an error overall. It looks like, but is not the same as total probability. Okay, so let's go ahead and calculate my probability of error. That's going to be 0.1 times 0.5 plus 0.2 times 0.5, and that is 0.15 or 15%. So what that means is each bit on the receiver end is 15% likely to be detected in error. Every bit has a 15% chance of being detected in error. If I transmit a 1, it's 15% likely, on average, that I'm going to call it a 0, and vice versa. This does not say that 1 bit out of every 15 is in error. All right? So, the last thing is, what's the probability of successful transmission? That's clearly 1 minus the probability of error. And in this particular case, it's 85%, which is 1 minus 15%. should follow quite naturally. So, we did 3 examples today, looking at no new information really. We didn't introduce any new concepts. We looked at the Monty Hall problem and a couple of other problems that use total probability and Bayes' theorem. So, that's all I have for you for today. As always, if you have any questions, please let me know and I'll answer them to the best of my ability. Have a nice day. Bye-bye.